Hello, hello, hello. Welcome, everyone, to the final installment this week. I want to give everyone a huge round of applause on all the work that you've been doing because it has been extremely quality. And it seems that everyone, for most of the material and I would say over 90% of the content, you're understanding it, which is amazing to see, especially since we're doing this over distance, So I'm very, very happy and I'm proud of everyone with all the work they've been doing. It's been like top notch, really good. Happy. I did update everything and check my progress. So if you have any gaps, you can look there to see what you haven't handed in. You can also look on the classroom itself because for the folks who have handed in any homework assignments, I have marked them and I've returned them. So there's two different avenues to check there. If you haven't seen your stuff graded on either of them, please hand them in so I can give you a grade on that. And we're not going to have a quiz this week. We're just going to do this final installment here for the week. And next week, we will have the second major quiz for this unit, which will likely be the last quiz for relations and functions before we move on to the next major unit. So there's probably only going to be about two quizzes for this. And if you have to bomb it, just shoot me a message and we can do a rewrite really quick. Okay, so we're picking up from last time. And last time we finished talking about inequalities. And last two things we have to touch on are continuous domain and range and interval notation. So let's jump right into what continuous domain and range actually are. Before we can actually talk about what they are, we need to identify a big difference between the data that we've been looking at so far. And the data that we've seen in everything in the past mainly has been, it's called discrete data. And discrete data essentially is just, it's essentially data that is, we could say organized purely with ordered pairs, So we see up here, this data is discrete because the only data points that we see on here are just these blue ordered pairs that are poking around. And we can label them if you want and go through them. We don't have to do that, but you could for sure label them and those would be your discrete. So in terms of the relation, these are the only points. So there's 1, 2, 3, 4, 5, 6, 7, 8. These are the only 8 points in the relation. Continuous looks a little bit different, right? Well, we see that we have no points on this graph, technically no points. And we just have one long continuous kind of curvy line here extending from the bottom left quadrant to the top right quadrant. And the big difference between a continuous data set and a discrete data set is that a continuous data set, we can think of it having having an infinite amount of points, an infinite set of well, we'll just say points. I don't want to get all too buried down in the jargon of this. Continuous infinite set of points. And we say that it's infinite because for one, this graph, it's extending past what the limits I can put here for our grid. So it's extending outside of this graph here and extending all the way up here. But more so, it's also continuous because there's technically a point at every single part along this graph. So we have 0, 0 here, then it goes like -1, or sorry, negative 0 point something, negative 0 point something, negative 0 point something. And we have a point everywhere along this graph. And then if you think about it even deeper, well, then we technically have points in between points. There's a point in between. If we say that we have a point here, we say that we have a point here. Well, there's actually points in between that. And so in between these 2 points, there's also points in between that. And then in between those 2 points, there's points in between that. And you can see how this gets super messy really quick. There's just a lot of points. And that's why we say it's continuous. It has a continuing range of values that we can put on a grid. And so we've seen ways on how to define our domain and range for discrete points of data. So what we usually did for defining the range here, we do domain equals, we do our funny little bracket, and we would just list off all the x values. So in this case, let's just do these really quick. We have -1, 2, 3, 4, 5, 6, -6, -4, -2, 0, 2, 4, 5, and 7, it looks like. And then for our range, it was the same thing, except we just plug in our y coordinates, right? And so that would be -1, 0, 1, 2, and 3 for our range. When we're listing our domain and range, though, for a continuous function, we just have to do something a little bit different because you would not have any time in the whole history of your own life to write out the domain of a continuous function. It would just be going on forever and ever. You would never reach an end. So what we do instead, we do a little trick. And here's how it works. Let's say we want to find the domain of this function up here. First, we ask ourselves, are there any x values where this graph will never actually touch? are there any x values where this graph will never actually extend to? So this is extending forever and ever and ever, all the way out in this direction. There are no limits on where this can spread, and it's extending forever in the left direction or in the negative direction. There are no points that this will not eventually hit, right? So what we're going to say, what we always start off with saying, we draw our squiggly brackets as we do. And what we say first is that x, and we're going to do a little special symbol here, is an element. This means an element. And then when we're talking about continuous functions, what we're going to say is that we're going to be talking about all the real numbers. So every single number that is possibly exists within this graph and even outside of it, we're going to say that x is part of that real number set. And to rewrite the real number set, you do this kind of little fancy R. It's like an R with an extra little backbone for support. So x is an element of the reals. And then we're going to do another special little symbol here. And it's literally a straight line. And that straight line means such that, or sorry, actually, no, we don't actually have to do that one yet. If our graph is extending to every single possible direction, this is all we need to say. X is an element of the reals. And we close our brackets, and that's it. So this is just basically saying that it's everywhere. X is everywhere. It can touch every single point in the negative and in the positive direction, okay? And for a range, we're going to ask ourselves the same question, except this time instead of x, it's going to be y is an element, but we're going to ask ourselves a question. Is there any y point on here that will never be touched? Well, no, because it extends both in this positive y direction forever and extends in both this negative y direction forever. So it will always touch every single y value at some point. So y is also an element of the real numbers. So let's actually define some of those terms there. So we could say that this one is an element of, and this is real numbers. You can have other kinds of numbers like natural numbers, imaginary numbers, other stuff like that. But for our purposes, it's always going to be real numbers. So I'm going to expand on this more in a little bit, but let's move on and let's talk about interval notation. And essentially, it's just another way for us to notate our domain and range. And the way that it works is we're going to call them soft brackets. And soft brackets are essentially your like normal parentheses. Your normal parentheses. I'll do this a different color. So like that. And then hard brackets are, well, it's like, I don't know, putting a backbone on those soft brackets. It's like square. Also, we can call them square brackets. Actually, that might be better. Square brackets. And there's not too much more to understanding interval notation until we see an example here. So let's say that we were given this circle here on the graph and we were asked to identify the domain and the range using interval notation. So what we're going to do, we're going to set this up the same again. Domain equals D for domain. But in this time, instead of opening up the squiggly brackets, we're not going to do that. We're going to use either our soft brackets or our hard brackets. So the domain of this circle, we're looking at just all the x values that are within this circle's reach. And we see that, well, the far left x value, it'll touch it at, let's see, this is, what point is this? -1, 2, 3, 4, -5. And the far right is 1, 2, 3, 4, 5, as it should be. +5. And let's just get our y axis here too. So the 1, 2, 3, 4, it's +5 here. And we have -5 over here. 1, 2, 3, 4, 5. Okay. So let's look at our domain first. So just our x-axis here. So we can see that our circle, everything within it lies between -5 and +5, right? We have this line here. And normally, if we don't have a circle notation like that filled in and the open circle that we had before, and it's just like this, you can assume that the circle includes -5. Same here, includes +5, and same for everything else. So you can treat it like we're basically assume it's a closed circle. Assume closed point for a domain. And the way that we're going to write this, well, if we're going to assume for a closed point on our domain, our closed point, square brackets, is we're going to use the square brackets. So this is for the closed circle, or includes a value. And then this one is going to, you can guess, is this was the open circle. Does not include value. It includes everything up to that value, does not include value. So this one, since our circle is, we're assuming that it's going to pass through -5, we could say that our domain is going to be, let's start out with, open our hard bracket. It's going to be between -5, and then we're going to put a comma. And then the way that interval works, it works as a range. So it's between -5, and then what's the next highest? Where does it become not, or what's the next limit on our domain here? Well, it's +5 over here. So it goes from -5 to +5. And since it includes +5, we put another square bracket at the end. Okay. Well, our range, it's going to be the exact same, right? Because our lower end of the range is this -5 here. So we have -5, and our upper range is +5. So you're always going to list these from lowest to biggest. Range is +5. So we're using those square brackets because the circle is including those points. It's including those points. If no circle is written there, or open circle or closed circle is written, you can assume that it's always including it. So let's go look at another example down here, something that's a bit different. And let's identify the domain and range of this one. Let's start with domain. Domain of this one. So we see that our far left portion occurs at our x coordinate for this one is 1, 2, 3, 4, 5. This is -5 here again. And our far right coordinate, let's see, 1, 2, 3, 4. It's 5 again. I did not mean to do that. But notice on this graph that we start to have those open and closed circles, right? So if we were to find the domain for this one, we'll start with our lowest value of -5, and we're going to be using a soft bracket, right? Because this open circle means it's including everything up to, but not including -5. So we're going to throw in the soft bracket, -5, and then we go to the end of the function over here, and it's a closed circle. So we're going to use +5, but then a hard bracket. So you see how we have a combination. We have a combination of both hard and soft brackets. And you might get that sometimes. So let's look at the range now. Range, well, let's see what the y value is touching there. So 1, 2, 3, 4. This is +4. And then down here, it's touching 1, 2, 3, 4, 5, -5. And so again, let's start with our lowest value. And since our lowest value, so look at this one, our lowest value is including that -5. So we're going to start out with a hard bracket, -5, all the way up to, we see that it includes everything up to +4. But it doesn't include 4 itself. So 4, soft bracket, just like that. And actually part of this, I need to just modify this a little bit because technically it does go below 5 here, right? This part is going below 5. So let's just fix this just so it's a bit more consistent with what I'm talking about here. If you caught that, nice job. A+ for catching my follies. There we go. That's a bit better. So again, we have that combination of both soft and hard brackets there, depending on what's included and what's not included. Let's look at this one here. Let's look at this one. Let's use identify domain and range. And since we have a continuous function like this, we can't really use, well, we can use interval notation. We can use that. But what I'm going to use first, I'm going to use just the regular, the notation that we used before with that element of the reals, okay? So let's start off with domain for this one. Domain. And what we're going to do, we're going to open up our squiggly bracket. And let's say that we're going to always say that x is an element of the reals. We'll always say this. And we're going to ask ourselves, is there any x value that this curve will never touch? If we extend this out forever and ever and ever, will it ever not touch any x value? And well, for this one, again, not really, right? It's always going to hit every single x value. So our story stops right here. X is an element of the reals. Let's look at our range though. So we're going to start out with the same. Y is an element of the reals. But I'm going to ask you the question, is there any y values on this graph that this curve does not touch? And you think about that a little bit. It's like, yeah, look at the whole top half of this graph. This curve will never ever touch these top halves because it's continuously growing down like this, right? So what we need to do in a case like this, we add a new little symbol, and it's just a straight line just like this, and it's called such that. So y is an element of the reals such that, and then here's where we need to use our inequality. So where is y defined in this graph? Where is y defined? Well, let's figure out the smallest point where it's defined. And the smallest point occurs right at 0, 0, right? This is 0, 0. This is where you could think of the curve branching out from. And so what we're going to say is that y is an element of the real such that, and then what we're going to do, we're going to use an inequality. We're going to say that y has to be less than or equal to what? Less than or equal to what? Well, it has to be less than or equal to its smallest value, or its biggest value technically, of 0. And then that's it. We close it with our fancy bracket, and that is it. So y is an element of the reals such that it has to be less than or equal to 0, because it will never be bigger than 0. It's always going to be less than or equal to 0. Okay. If you wanted to do this with interval notation, and I would always leave this up to you as to how you want to define domain and range. You can use whichever method you prefer, but let's look at interval notation for this. So our domain, well, we can't really say it has any endpoints, right? Because it's a continuous function. So we could say that it goes, what's the biggest number you could think of? Well, only infinity, right? So we could say that it goes, and always infinity, if we're writing infinity, it will always be in a soft bracket because you can never actually hit infinity. It's more like a philosophical question, you know what I'm saying? And so if we think about, well, what's the smallest number? What's the smallest negative value or the biggest negative value that you can think of? Because that's the way this is going to grow on to our left side here, a negative portion of our graph. Well, it's just going to be negative infinity. And then where's the highest point it can go? Well, think about it enough, you get just positive infinity. And you close it off with a soft bracket. That's it. But what about our range? Well, our range, let's just see what our time is at here. Oh, we're good. Our range can go from, where's the highest point that we could find? Well, actually, let's think of the lowest point first, because that's what I've said before. We always start with our lowest point. So the lowest point that it's ever going to hit, well, it's going to go extend down forever and ever and ever, right? So the lowest number you could think of is negative infinity again. And it's going to extend all the way up to, what's the highest value? Well, highest value is that it's at 0 point there, right? And it also includes that 0 point. So we need to put a hard bracket there. So it goes from negative infinity to positive 0 and includes 0. And actually, let's label that. We have to do that. Let's do this. This means such that. And this is essentially all that we need to have covered for the end here. Just that interval notation, defining domain and range for those continuous values there. And that is it. Should we do one more question here? Yeah, let's do one more. I don't like how many. Let's just set up a quick grid here. Let's do one more. Okay. So example. Determine if a function, determine if this is a function and the domain and range. Okay. So let's set up our grid here. I promise this last example will not take too long. Let's define this is our y-axis, this is our x-axis, and sorry everyone for the awkward cut there. There was a small glitch with my microphone that wasn't working. I'm just going to erase everything that I went up to at that point before I realized that it glitched. Okay, sorry. So let's go back to this question here. Final example here, and we're asked to figure out first, if this domain is a function. And what we can do, we don't need to do our whole mapping of coordinates and the very brute force way of doing it. We can just do our simple vertical line test. And what we can do, we're going to draw vertical lines throughout the course of this relation here. And what we're going to look for is if it passes through the blue line or this blue relation more than once, that means that it is failing the vertical line test and it is therefore not a function. So what we've done here, I've drawn a few vertical lines from left to right here. We can see that it's passing the test so far, going through just one point of the blue line. But hey, let's look at this right here. We have the single x value where this line is, and we can see that it's passing through two different y values, right? It's passing through, it looks like just under +1, and then I think this is just right at -6. 1, 2, 3, 4, 5, 6. Yeah, this is just happening at -6. So for this x value of 1, 2, 3, 4, 5, 6, 7, there are two values for that. So remember how we said that is breaking the rules. If we have those two domains, this is our x domain, this is our y domain. There was a 7 here, and it looks like it's mapping to just over 1, or just under 1, and a -6. So that was where it's breaking that rule there, right? And we can't have that. Breaks rule. So what we could say is therefore, since this fails the vertical line test, just going to call it VLT, it is not a function. But even if it isn't a function, we can still determine its domain and range. So I'm going to do this in two ways. I'm going to determine the domain and range in interval notation first. Interval notation. And let's set this up as before. So let's figure out the domain. Let's figure out where this function is defined all along the x-axis. So we see that the x-axis, let's go to my highlighter. We see that the x, oh my gosh. It's really, I can't draw on that. Okay, that's fine. Thought the highlighter would work. Okay, well, let's use this. Let's use this green line to help define where the domain starts and ends. So the domain is starting over here, right at that -9 point. And you might want to be like, hey, there's a endpoint right there. That's where the domain ends. But it doesn't end here, right? Because this curve loops right around. So the domain actually ends right where this curve kind of peaks. So right here. And let's figure out what point that is. What point is that? That is, it looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is positive. This is positive 10. So how can we, and again, if we don't have an open or closed circle here, we can assume that 10 is included. So let's look at our notation here. Our domain is going to include -9 at a far end. So we're going to use that square bracket, and it's going to go up to positive 10. And again, square bracket at the end to show that we're including it. What about our range? So again, let's start with our lowest value for our range. Our lowest value looks like it's this one right here, which I think was -6. 1, 2, 3, 4, 5, 6. -6. And it's open, so that means we're not including it. So we have to use a soft bracket. -6. And then it goes all the way up to, what's the max value? It looks like the max value is positive 1 here, right? And it includes positive 1, so we have to use a hard bracket for that one. 1, hard bracket. We can use this with kind of set notation instead if you wanted to. And I would specify an assignment if I wanted you to do one or the other. So set notation, let's look at domain. We're always going to start it off. That fancy bracket. We're going to say x is an element of the reals. Okay. And let's figure out, where is x defined in this case? Where is x defined? Because x isn't defined everywhere. X is only defined between those 2 points that we said, -9 and positive 10, right? So what we can say, well, we're going right back to our inequalities. So x is an element of the reals, and then we have to put the such that clause because it's not defined everywhere in x. And we're going to set up that inequality. We're going to say that we'll put x in the middle. Since we have two parts here, two parts of this domain, we have to set up two sides of x. So let's look at the left-hand side. X has to be bigger than or equal to, right? Bigger than or equal to, because we have that filled in circle there. So our left-hand side, x has to be bigger than or equal to -9. And then it has to be also less than or equal to positive 10, right? And we're assuming that it has to be less than or equal to because we don't have any circle filled in there. So we could say that it includes 10 itself. And we'll finish it off. And that's it for the domain there. Let's look at the range. Again, set this up. Y is an element of our real numbers such that, because our range also, it's not defined everywhere on the y-axis, right? It's only defined between right here and then up here. So let's look at our lowest one. Our lowest one we said was -6, but it doesn't include -6, okay? So we have, let's do, oops, not x anymore, it's y. So our lowest one, we say that y has to be bigger than -6, not bigger than or equals to because it doesn't include 6, and less than what? It was positive 1, right? Less than or equal to positive 1. And that is it, folks. So we only have, I think it's 2 more parts that we have to cover for this unit. We'll definitely be done it by the end of next week. I hope this was informative, and sorry for the cut there. I know it was a bit awkward, but I will post the assignment for this. Please have that completed by the end of the day, ideally, but I realize that you folks have other classes, and I don't know what the stress like is with those, but please, keep on doing amazing. You guys are absolutely killing it right now, and I'm really, 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 like, from the bottom of my heart, so happy that everyone's getting this, and especially for the folks who were struggling a little bit before, and you're seeing you kind of flex those math muscles now. It's great to see. I'm so happy. Okay. Have a wonderful weekend, everyone, and I'll see you on Monday. Bye.